The next thing we're going to take a look at is the signal intensity in an IR spectrum. In other words, if a molecule does absorb a certain energy of light and a signal is produced on an IR spectrum, how intense is that signal going to be? Or how much energy does it absorb? So one of the main things we need to consider has to do with the polarity or the dipole moment of a bond. So for a bond to absorb IR radiation, there must be a change in the dipole moment during that vibration. So if a bond is nonpolar because of symmetry, IR light isn't going to be absorbed and that vibration is said to be IR inactive. So let's compare a couple of alkynes. And specifically, we're looking at the carbon-carbon triple bond stretch. In this first one, we have a terminal alkyne. There's really no symmetry here. We have a good carbon-carbon dipole. So this is going to absorb IR light, and that is going to be IR active and give us a nice signal on the spectrum. However, if we move to this symmetric alkyne, we have a plane of symmetry that runs through the carbon-carbon triple bond. This molecule doesn't have a dipole there, so it's not going to absorb IR light, and this carbon-carbon triple bond is said to be IR inactive. Another thing we can consider is the fact that a larger dipole is going to mean a more polar bond that also is going to mean a stronger absorption. So here we're going to compare a carbon-oxygen double bond to a carbon-carbon double bond. In the carbon-oxygen double bond, we have a pretty strong dipole going from the carbon to the oxygen. This absorbs IR light extremely well, and it gives us a very intense absorption. However, if we have a carbon-carbon double bond, at least one that's not symmetric, so these could be whatever, R groups coming off the carbon or hydrogens coming off the carbon. Even in an asymmetric system, we still have a carbon double bonded to a carbon. There's not going to be a very large dipole here. That means this IR absorption is going to be much smaller and much less intense. So if we want to compare XH bonds, whether it be oxygen, nitrogen, or carbon-hydrogen bonds, if we have a more polar bond, so OH is more polar than NH, which is more polar than CH, well, this stretch corresponding to the OH is going to be more intense than the NH. And then the stretch corresponding to the carbon-hydrogen bond is going to be the least intense because it's the least polar. Now let's just compare a couple of heptene isomers. And what we'll eventually learn is that the carbon-carbon double bond stretch generally appears around 1650 on the IR spectrum. So that's right around in this region. Now 1-heptene, there's not a lot of symmetry here. We have two hydrogens, it's a terminal alkene, and we actually end up with a pretty strong absorption in the 1650 region. However, when we go to 3-heptene, we still have a carbon-carbon double bond, but this molecule is much more symmetric. And although there's still a little bit in that region, a stretch corresponding to that carbon-carbon double bond is almost non-existent. So that's something you really have to watch out for. Just because you don't see a certain stretch doesn't mean this functional group's absent. That just means it's very symmetrical